Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is modular arithmetic. Okay, so the first thing I want to ask is what actually is modular arithmetic? And to answer that, I firstly want to answer the question, what is the difference between arithmetic and algebra? What actually is meant by arithmetic? Because this is often something that people get confused by. What does arithmetic mean? What's the difference between arithmetic and algebra? Well, the problem is that this is very difficult in modern algebra. In modern algebra, in abstract algebra, arithmetic has died. The use of the word arithmetic has died. It's something that was used in classical algebra. There was a nice answer to what the difference between arithmetic and algebra was in classical algebra. Whereas in modern algebra, in abstract algebra, the term algebra has swallowed the term arithmetic, and arithmetic has been encapsulated into algebra. But let me just outline then, in classical algebra, in the good old days, what was the difference between arithmetic and algebra? Okay, so let's have some basic examples. So remember, classical algebra is all about the classical number systems. So about the ring of integers, the field of rationals, and also, of course, the field of the real numbers as well, but mainly the ring of integers and the field of rationals. The number systems which you learned in primary school when you were about 10. Okay, so let me give you then an example of an arithmetic problem with let's go for the integers, the ring of integers, and then I'll contrast that to an algebraic problem in the ring of integers, and this is in classical algebra. Okay, so an arithmetic problem then. So to give you a nice real-world example, so let's say I have some job. I'm going out and I have some job and I'll earn some money. Okay, and when I come back home at the end of the day, my father has said that as a motivation for me to get a job, he will double the amount of money that I've earned. So whatever I've earned in the day, he'll give me an equal amount to that, so that overall my money doubles at the end of the day. Okay, so let's say I earn £5 in the morning, and let's say I earn £3 in the afternoon, and then I come back and my father doubles the money. An arithmetic problem is then, how much money do I overall have at the end of the day? Well, of course, what you'd do is you'd add 5 to 3, okay, so £5 was the amount I earned in the morning, £3 was the amount I earned in the afternoon, so that's how much I've overall earned when I return home, and then my father adds in an equal amount of money, so he multiplies this by 2, so that's the overall amount of money that I will then have at the end of the day. Okay, so 2 times 5 plus 3, and of course you can work that out and you'll get the answer 16. Okay, that's an arithmetic problem. You just need to use the addition law and the multiplication law on the ring of integers here to work out how much money I've overall got at the end of the day there, 16. Okay, now let's have a different problem then now. Let's now have an algebraic problem. So this is arithmetic. Now I'm going to contrast this to an algebraic problem. So algebra then. An algebraic problem would be to say, okay, I want to set how much money I want to earn. I wake up this morning and I decide I want to earn £20. I need £20. Okay, and let's say I have quite a bad morning. So let's say in the morning I only earn £2. The question is, how much will I have to earn in the afternoon if I'm going to earn overall £20 there? Okay, this is a different kind of problem. This requires algebra, so the way we do this is we'd say, okay, I don't yet know how much I need to earn in the afternoon, so let's just call it x. So we'll add 2 and x together to get how much I overall earned in the day, and then I'll have to multiply this by 2 to say how much I'll have by the end of the day after my father's doubled the amount of money, and that will need to equal 20. And you can see that in order to solve this problem, you're going to actually have to perform manipulation. Okay, this isn't as trivial as this. This you just had to apply how to add integers together and how to multiply integers together, and it would spit the answer out. This, it's different. You have to somehow manipulate this, and this is quite difficult to do. Well, obviously, the answer, I hope you can agree, is 8. Okay, I'll have to earn £8 in the afternoon if I overall want to earn £20. But think about how difficult this is to do as an actual algebraic problem. If it wasn't so familiar to you, as an algebraic problem, it is actually quite difficult, because you might say, well, just multiply by half, but if we were working in the ring of integers, there's no such thing as a half. Again, that really shows you how powerful the extension of the integers to the rationals actually is, because then there would be a nice way of manipulating this to actually work out what x is equal to. But I hope that communicates the gist of what the difference between arithmetic and algebra once was. Algebra was all about having to perform manipulations to an expression like this to actually get the answer, whereas arithmetic, it was already, this was the answer here, if you like, the answer, which we could call, let's say, y, how much you earned at the end of the day, was already on its own on this side, so you didn't need to perform any algebraic manipulations. All you had to do was plug in the numbers into the addition and multiplication laws on the integers, and that was just arithmetic then. So this is the difference between arithmetic and algebra in classical algebra, or at least in classical number systems such as the integers or the rationals. Arithmetic is just applying the addition and multiplication laws defined in those number systems. Algebra was applying manipulations to expressions like this to actually get answers in terms of arithmetic operations. Okay, right, so that was what the difference between arithmetic and algebra was in the good old days. Now you might think, okay, so arithmetic is just the study of the actual addition and multiplication laws on these sets of symbols, whereas algebra is the study of how it can be manipulated. Okay, so yes, we can apply this in modern algebra brilliantly, but people don't use it that way. Okay, people would never ever call the study of a composition law in group theory arithmetic. So no one would ever refer to group theory as arithmetic. Neither would they refer to linear algebra as arithmetic. Vector spaces wouldn't be referred to as arithmetic. Arithmetic is a dying word, basically. It's something that we only nowadays use in the context of the integers and the rationals, and we use it because it was used historically, and no one wants to change the terminology. So it's only used in the historical context in the classical number systems. We don't now use it in the modern number systems, such as group number systems or linear algebra. Okay, instead, algebra has now grown and it has swallowed arithmetic. So algebra now, in abstract algebra, algebra is just the study of sets of symbols with composition laws defined on them that usually have to obey associativity, and that's what algebra is. So indeed, algebra has become arithmetic. Arithmetic has been swallowed into algebra. Algebra no longer just is about these manipulations, it's also about the actual number system structure as well. Okay, so algebra as a term has grown and grown and grown, and arithmetic's been pushed out. So in modern or abstract algebra, algebra is the big term, arithmetic has died. We only nowadays use arithmetic because of its historical use, and it's used in the context of when we're talking about the integers or the rationals. Okay, so that's what arithmetic is then. Okay, so modular arithmetic then, it's all about the integers. It's all about new number systems that we can build from the integers, hence why it's got the word arithmetic in there, because it comes from the integers. It's something that was conceived of in the classical era. Okay, so firstly then, let me just remind you of the ring of integers just briefly, and then what we'll do is discuss how we are actually going to construct new number systems, new rings from the integers, and we're going to do this by quotienting the ring of integers out by ideals within the ring of integers. Okay, so the ring of integers then. So first and foremostly, the ring of integers is just a set of symbols, so I'll draw these here. So you have 0, 1, -1, 2, -2, etc, etc, all of the whole numbers in a great big set here, and we have a great big addition and multiplication laws defined on this set of symbols, and they are defined in the normal way, in the ways that you learned in school. Okay, so that's the ring of integers, and what we're now going to do is we're going to quotient this ring of integers out by ideals within this ring. Now remember, the ring of integers is a commutative ring. It doesn't matter which way round you multiply two elements, the answer is the same. So what we now need to study then is what are the ideals in the ring of integers? What are the things that we can use to quotient the ring of integers out by? Okay, so remember, an ideal of a ring needs to obey two properties. It needs to be an additive subgroup, and secondly, it needs to be closed under multiplication by any element in the larger ring. Okay, so what we're going to first address is the additive subgroup part, okay, because from our experience of group theory, we know what the additive subgroups of the ring of integers actually are, but I want to remind you of that here. Okay, so let's discuss additive subgroups of the ring of integers. So for now, just imagine this set of symbols here as having the addition law on it. I don't really need the multiplication law at the moment, although actually in the explicit statement of these subgroups I'm going to use multiplication. But we want to now find additive subgroups. Okay, so I claim all additive subgroups are of the form n times z, where n is greater than or equal to 0. And let me just make it explicit what I mean by this. So n times z here means all integer multiples of this positive, or rather not necessarily positive, non-negative integer n here. Okay, so this means all things of the form little z times little n, where little z is an element of the integers. Okay, so to make this even more explicit, I'll write this out. So we want to go through every single integer, 0, 1, negative 1, 2, negative 2, 3, negative 3, etc. And we want to multiply that integer by our fixed integer n here. So we'll get overall, so we'll start off with 0, so when we put 0 in for little z here, then we'll get 0 times little n will always equal 0, so we'll get 0. Then when we put 1 in, we'll get little n. When we put in negative 1 for little z here, we'll get the additive inverse of n, so we'll get negative n. When we put in 2 here, we'll get 2 times n, so n plus n. Okay, and it will go on negative 2n, 3n, negative 3n. So this explicitly is what this is going to look like. Okay, so I claim that all subgroups of the group of integers under addition look like this, and that's one of the things that I want to remind you of the proof of firstly, and then what we'll show is that these subgroups are actually all ideals. Okay, so actually just before we do go on to the proof that all additive subgroups of the ring of integers are of this form, let me just give you a few examples of these sorts of subgroups. Okay, so if we for instance choose as our n 0, then we'll have 0 times z, and what we'll do then is multiply all of the integers by 0, and of course when you multiply all integers by 0, the answer will always be the same. You'll get 0 again and again and again. So in this set here, the only element of the ring of integers that you'll actually end up with is going to be 0. Okay, so there's an example. 0 times z is equal to the subset that just contains the additive identity. If we then look at 1 times z, okay, so I've now picked as my little n here 1, then what I'll do is substitute in for little n here 1, and then I'll take all integers and multiply them by 1, and of course when I multiply all integers by 1 I just get the integer back again, so I'll end up getting the entire set back again, so I'll get the entire ring of integers. So 1z is the entire ring of integers. To give you another example, 2z, so we're gradually going up and up and up. So 2z, what you'll want then is all the integers multiplied by 2, so this will be all the even integers. So you'll have 0, 2, negative 2, 4, negative 4, etc. Okay, so there's another example, and then you can imagine going on, so you can go on to 3z, which will be all the integer multiples of 3, so 0, 3, negative 3, 4, sorry, not 4, 6, negative 6, 9, negative 9, etc. And then you can go on to 4z, 5z, 6z, all of those are going to be different subsets of the ring of integers. Okay, now, what I want to show then is that firstly, these things are all subgroups, and then what I want to show you is that actually all subgroups of all additive subgroups of the ring of integers are of this form. Okay, so how can we do that then? So firstly, let's prove that these are always going to be subgroups. Okay, so to prove that something of this form, n times z, is always going to be a subgroup, what we need to prove is that it's closed under addition, that it has the additive identity in always, and that it has additive inverses in. Okay, so remember, to be a subgroup, it has to be a group in its own right when you view it as a set in its own right with the restricted addition composition law on it. Okay, so we need to check the axioms of group theory, but we don't need to bother with associativity because it automatically gets that from the associativity that was true on the larger composition law. Okay, so let's have a look then at this subset here and try and understand why it's going to obey the axioms of an additive subgroup. Okay, so firstly then, I want to show that if you add any two of these together, you will end up with another element that's back in here. Okay, so hopefully that is apparent, because any two elements within this subset are going to be integer multiples of this element n. Now when you add together two integer multiples of this element n, you'll get another integer multiple of that element n back again. Okay, so for instance, if you take z1 times n and you add it to z2 times n, okay, so these are two arbitrary elements from this set here, where z1 and z2 are both integers, what you can do is apply the fact that multiplication distributes over addition, and you can factor out the n here, so you'll get z1 plus z2 times n, like so. Okay, and of course z1 plus z2 is just another integer, so indeed this will be something that's back within this set. So I have now shown that if you add any two elements of a set of this form together, you will get another element that's back within that set. Okay, so axiom number 2 then of group theory is associativity. We don't need to worry about associativity because it's just a subset of the entire integers, and the addition law on the entire integers obeys associativity, so the restricted addition law down to this subset will also obey associativity, so we don't need to worry about that one. Axiom number 3 is that the additive identity needs to be in the subset. Well, there it is. Always it will be in the subset, because you can just, when you vary through all of the integers in this place of little z here, one of the integers that you'll put in there is going to be 0, and indeed, when you multiply any integer by 0, whatever you've got as n here, you'll always get 0 back again. So every single one of these, no matter what little n is, will contain the additive identity 0. So that's axiom number 3 satisfied. And then additive inverses. Why would it contain additive inverses? Well, look at this. We've got n and negative n, 2n and negative 2n, 3n and negative 3n. Those are going to be each other's additive inverses, so it will contain additive inverses. Okay, so indeed these are additive subgroups, and indeed they will be commutative as well because of commutativity on the addition law for the larger integers. So these are commutative subgroups. Okay, right, so that's the first part shown. All of these subsets of this form are subgroups of the ring of integers. Okay, what we now want to show is that they are the only additive subgroups, i.e. that there are no others. So what I want to show is that if I have an additive subgroup of the ring of integers, so let's take H, which is an arbitrary additive subgroup of the ring of integers here, what I want to show is that it is one of this form, that it is always going to be of this form. There is always going to be some little n such that h is equal to n times z. So what I want to show is that h is equal to n times z. So how does this work then? Okay, so there are two cases here. The first case is that this subgroup capital H just contains the additive identity element. That is a possibility. Okay, so there is one possibility, which is that the subgroup capital H is just equal to the subgroup that contains the additive identity, the trivial subgroup, which just contains the additive identity. Okay, so that would then mean that it's writable in this form, 0 times z. Okay, so indeed, it's true that if it is just this subgroup which contains only the additive identity, then it is writable in this form. The other possibility is that it contains more elements than just the additive identity. Now, any subgroup always has to contain the additive identity, so we can always start off by saying it will have the additive identity in, but let's say now it contains some element beyond just the additive identity. Now, either this element is a positive integer, okay, or it's a negative integer. But what I want to show you now is that this subgroup that contains more than just the additive identity will always have to contain a positive integer. Okay, so what I want to show you is that any subgroup that contains more than just the additive identity always has to contain a positive integer, i.e. that it cannot just be a subgroup made up of non-positive integers. It can't just have negative numbers in, basically. Okay, and the way that you can show this is either this x is positive, in which case you have a positive integer in here, or it's negative, but if it's negative, its additive inverse will also have to be in there, and its additive inverse will be positive. Okay, so the subgroup here that contains more than just the additive identity element has to contain positive integers. Okay, so I can always say that this subgroup that contains more than just the additive identity element will contain positive integers. Okay, now why is that helpful? Well, now what I can say is pick the smallest positive integer in capital H. Okay, so I've now said that if capital H is going to be beyond just the subgroup that contains the 0 element, then it must contain positive integers. So there must be a smallest one. Now let's say that x is the smallest one. So what I claim then now is that H is equal to x times z. Okay, so if you've got a subgroup that is beyond this subgroup, i.e. it contains more elements than just the additive identity, then it will always have to contain positive elements, and you can therefore pick the smallest one. We are now calling that smallest positive integer x here, and I am claiming that h is of the form x times z. Okay, right, so the first thing then to show is that all of the elements of x times z have to be within H. So I want to firstly show that this has to be a subset, or rather a subgroup, because we know that anything of this form will be a subgroup. So I want to show that it will be a subset, at the very least, of H. Okay, so I want to show that all elements of this will be contained within here, and then my next move will be to show that nothing that is not of this form can possibly be contained within this subgroup capital H. Okay, so why is it the case that all of the elements of x times z have to be within the subgroup capital H? Well, the instant you've got an element x here, you have to have all integer multiples of it, and the reason is that this subgroup has to be closed under addition. Okay, so that means that you're going to have to contain x plus x, so you're going to have to contain x added to itself, now that's 2x. You're also going to have to contain x plus x, which will be 3x, etc. So you're going to have to contain all of the positive multiples of x, and then you're going to have to contain all of their additive inverses, because you're a subgroup. So you're going to have to contain negative x, negative 2x, and also negative 3x, and on and on. Okay, so indeed you are going to end up containing all integer multiples of x, and we know of course that you've already got the additive identity in there, so you'll have 0 times x. So there's the simple explanation as to why the instant you put in x here, the instant we know that x is there, all of the integer multiples of x also have to be within that subgroup. Okay, so now what I'm going to show you is that no element that is not of this form is going to be in this subgroup. And I'm going to do this by proof by contradiction. So let's assume that there is an element that is not of this form. Okay, so let's assume, so let, what should we call it? Should I call it A? So let A be an element of this subgroup capital H, such that A is not an element of x times z. Okay, so A is something that's in capital H, but it is not an integer multiple of this element little x here. Okay, so how am I going to arrive at a contradiction? Well, the contradiction that I'm going to arrive at is that x was not the smallest positive integer in this subgroup capital H, which is a contradiction because I assumed that we had picked the smallest positive integer in this subgroup capital H. Okay, so how am I going to do this then? Well, what we're going to do is use the fact that we can divide with a remainder in the integers. Okay, so let me explain this in more detail. So if I draw the number line here, okay, so let's mark on the elements which are integer multiples of x. We'll have 0, we'll have x here, we'll have 2x here, we'll have 3x here, we'll have negative x here, we'll have negative 2x here, we'll have negative 3x here. Okay, so these are the integer multiples of x drawn here. I've tried to space them equally apart like so. Okay, now, if we've got some element a which is not an integer multiple of x, okay, so to draw a picture for this, I'm just going to put it on this picture, but of course it could be far away from what I've actually got here. I've only gone up to 3x and down to negative 3x. It could be far, far away. But to get the concept across, let's say it is here. So let's say this is a. Okay, so the fact that it is not an integer multiple of x means that it has not hit one of these red dots. It's in between the red dots. Okay, so that should be fairly intuitive. So here is our a here in green. Now, what we can always do is we can always go to the left of a, wherever it is, and this counts if a is negative as well. So if a is negative over here, people often get confused about this. They understand it for positives, but it also works if it's negative. Okay, so wherever a is on our number line here, you can always go to the red dot to the left of it. So if it's down here, it'll be this red dot. If it's up here, it'll be this red dot. So go to the red dot to the left of it. Okay. And what you can then do is you can say that a is going to be that integer multiple of x. Okay, so I'll put that as z times x. So some integer multiple of x. So if we had a here, that integer multiple of x would be 2 times x, so the integer would be 2. If a was down here, it would be negative 3, so the integer would be negative 3. And then you can have plus some remainder, which is going to be an integer, which is this portion here. This bit that you have to add on to your red dot to the left to get up to your green cross. Okay, down here it would be this portion here. Okay, and what can we always say about this remainder? Well, we know it's going to be an integer, so r is going to be an integer. We can also say that r is going to be a strictly positive integer. Okay, it's always going to be greater than 0 because I always chose the point to the left, and therefore we're always having to go in this direction to the right to go up to our point a. Okay, so I can write a as some integer multiple of x plus r. Okay, and the other thing to say is that we can also bound the size of r. Not only is it going to be greater than 0, but it's also going to be less than something. It's going to be strictly less than x, and this is important. How do I know it's going to be strictly less than x? Well, if r was equal to x, you would end up jumping from this red point to this red point. So for instance, if you took 2x and then added on a remainder of x, you jump from here to here. So if a is between 2x and 3x, that must mean that the remainder here is less than x. Okay, so the remainder is going to be strictly less than x there. Okay, and now this is important. Now, a is assumed to be an element of our subgroup capital H. We have now shown that z times x will also be an element of capital H. So that's this portion over here. Okay, x was an element of capital H, so all integer multiples of x were an element of capital H. So now if we consider what is a plus the additive inverse of z times x, that is equal to r in the larger ring of integers. Okay, but of course, this is an element of our subgroup, this is an element of our subgroup, because z times x was an element of our subgroup, and our subgroup is closed under additive inverses. Okay, so when you add these two things together, you'll also get something that's in our subgroup. This has to be an element of our subgroup because the subgroup is closed under addition, and both of these are elements of the subgroup. So that therefore implies that r, this remainder, is an element of the subgroup, but that's a contradiction because r was smaller than x and it was positive. So I've now found you some positive integer that's in capital H which was smaller than x, and I assumed that I had picked x because it was the smallest positive integer. Okay, so if you have picked the smallest positive integer in your subgroup capital H, then it must be the case that your subgroup is equal to x times z. It cannot contain any element that's outside of that, because otherwise you can prove the existence of something else in the subgroup capital H which had which was smaller than capital X, a positive integer that was smaller than little x rather. Okay, so that then is how we can prove that all subgroups of the ring of integers, all the additive subgroups of the ring of integers are of this form, n times z. Okay, so n times z, these are all the additive subgroups. Now, we don't need to worry about having n is a negative number. If you think about having n is equal to -1, that will actually give you the exact same subset as n is equal to 1, and the same with an arbitrary negative n. It will give you the same as just the n times z. Okay, so we don't need to worry about if n is a negative number. We only need to go over n is a non-negative number, and that will capture all of these possible subgroups. Okay, so these are all of the additive subgroups. So if we're looking for ideals, then this is all we've got. Okay, there are no other additive subgroups, and an ideal, first and foremostly, must be an additive subgroup, so we have to start looking at these. Okay, so what I want to now show you is that all of these things are actually equal to ideals. Okay, so I'll just write out once again what this equals. It's all integer multiples of this non-negative integer n here. Okay, so why then is this an ideal? Well, it's an additive subgroup. The next thing I need to check is that it's closed under multiplication by the larger ring of integers. So if you take any integer that's in the larger ring of integers and multiply it by an element in this subset, I need to prove that you get something back in the subset. Okay, so let's take an arbitrary integer. So let's say z prime is some arbitrary element of the integers. So I take an arbitrary integer here, and I now consider what z prime multiplied by an arbitrary element of my additive subgroup here is. So I take my arbitrary element of the additive subgroup, z times n, so z times n is some arbitrary element of nz here, and I want to show that the thing that I end up with here is back within n times z. Okay, so if this is going to be an ideal, this better well be back in n times z. Okay, that's just the definition of an ideal, that when you take an arbitrary element of the ideal and multiply it by something that's in the outer ring, that you get something that's back in the ideal. That's what we mean by closed under multiplication. Okay, so we can now just apply the fact that multiplication is associative, and we can turn this into z prime times, whoops, not z, prime again, just z there, and then times n. Okay, now of course if we multiply z prime and z together, we'll get some other integer. Okay, because z prime is an arbitrary integer, z was an arbitrary integer, so when you multiply two integers together, you'll get another integer, and therefore this is still an integer multiple of n, and therefore absolutely it is something that's in this subset of all integer multiples of n. So basically, when you take an integer multiple of n and multiply it by another integer, you do still get another integer multiple of n. That's very, very simple. Okay, so indeed, all of these additive subgroups, which are these subsets of all integer multiples of n, these are all ideals within the ring of integers. Okay, now, some new notation then, because these special ideals here, these ideals within the ring of integers, they are all very special. They are all actually principal ideals. Okay, so nz is actually the principal ideal generated by n. Okay, because what you have just done here is multiply n by all elements of the larger ring, which is the ring of integers. Okay, so in fact, all of the ideals within the ring of integers are principal ideals. They're of the form all of the elements of the ring multiplied by a set element of the ring n here. Okay, so as I've discussed, we have seen the principal ideal generated by 0, that was called 0z before. We've seen the principal ideal generated by 1, that was called 1z, and we've seen the principal ideal generated by 2, that was 2z, and you can continue on for n is greater than or equal to 0. Okay, these are all principal ideals. Okay, right, so the integers has only principal ideals. All ideals within the integers are principal ideals. Okay, so now here's the big question that is going to give us modular arithmetic. What happens, what number system do we get if we take the ring of integers and quotient it out by one of these ideals? So you can either use the notation nz, that's probably a bit more common, or you can use the notation z modulo out by the principal ideal generated by n. Okay, so we are going to form these quotient rings, and these quotient rings that we get by quotienting the ring of integers out by ideals, the only ideals within the ring of integers, these rings will be called the modular arithmetics. These are the modular arithmetic number systems. Okay, so in the next video then we will construct these number systems.